and then it'll run a basic simulation. With a couple examples. So hopefully that'll be useful. Okay, let's do it. Thank you, as always, for your feedback on the surveys. Someone actually said they want more jokes, and if it wasn't an anonymous survey, I would instantly give an A for that. But unfortunately, it was anonymous, and that person will. But it made me happy. Okay, today we're going to do the second half. Remember, I talked last time about a point finger, and with the promise that at some point we'd put the robot back in. And the goal today is to put the robot back in. And I'm going to do that in a few steps. I want to tell you about, unfortunately, there's a bit of a zoo of different manipulator control ideas. They are all I think, very related and very simple. So my task today is to try to keep that organized for you in your head on the board and try to make it so it's not confusing. Okay, and I'm going to try to do that by, I'll put the outline here and then go back to it a couple times, okay? So we'll do first just joint space control. And I want in joint space for you to just to lock in what it would mean to do PD control, what it means to do stiffness or impedance control, what it would mean to do inverse dynamics control. Okay, and then we're going to go into Cartesian or end effector space. And we'll primarily think about what it means to be doing stiffness or impedance control there. Okay, and I'll make sure I talk a little bit at the end about some limitations and extensions. Okay, so they're very related ideas, very simple ideas. I hope that by the end you'll understand the difference between those and then understand a beautiful trick about making the entire robot program the dynamics at the end effector. Okay. Now last time we did it on a point finger, and just partly to review that and to build into the next one, the interesting thing about the point finger case is that your joint space is your Cartesian space. So we did, in some sense, we didn't do inverse dynamics, but we did these, and I'll just write them again, and we'll launch from there, okay? So we thought about our robot as just having, being a point with some mass, okay? So the configuration of that was really just x, y, z position of that, okay? It turns out that I could have equivalently said that was the position of the finger, using my multi-body notation, the position of the finger in the world coordinates. And since we're going to go back and forth between joint coordinates and end effector coordinates, it's a weird thing that in this particular example, they're the same. Okay, more generally, those are going to be different, and we're going to want to go back and forth between them. But I'll highlight here that they're the same and just show the various components when they're the same are very simple. Okay, so the dynamics of this point finger were very simple. We just had our mass was our gravity vector. Let me write it in the slightly more general form this time. This is the gravitational vector. which for the simple robot is just 0, 0, negative m times 9.81, negative mg, if you will. Okay, and then we allowed ourselves to have some fictitious forces being applied. Like our actuator was coming in as like a jetpack, basically, that could apply forces anywhere. And then I could potentially have some external forces that were applied at the finger. And we talked last time about how to regulate the external forces, right? Either directly or indirectly. When you see this, by the way, the reason I always choose to write it like this, I've said this once before, I'll say it again because we're going to build on it today here, but I want you to see this equation, and the reason I always put some terms on the right-hand side, some terms on the left-hand side, is because I want you to see this as just mass times acceleration on one side. And these are all the forces, right? This is on the sum of the forces. So the gravity is a force, a torque, right? My control input is another force that's being applied on any external forces. So this is just F equals ma. Okay, and I will always try to write it where I have ma on one side and force on the other side, unless we start trying to be fancier. But the original governing equations should be like that. Okay, so in joint space, there's an interesting question, first, of how do I track a trajectory? So we talked about force control, and we'll get back to force control, but let's forget about interacting with the world. Let's just say I want to move my finger around, and I spent some time maybe with my kinematic trajectory optimization, made a beautiful trajectory, Q of t, okay? I've got some beautiful Q of t, I'll call it Q desired of t, okay? Maybe the result of trajectory optimization. There's a problem in the manipulator control world, which would just be trajectory tracking. Right? If I have some Q desired of t, how do I make it so Q of t tries to track, converges on Q desired of t, and maybe tracks it with high precision? And for this, I'll say the external forces are 0 for a minute, and we'll put those back in, okay? So what is a good controller for tracking a trajectory that you might want to run on a robot, okay? Even in the point finger case, it's just so simple that I think it's worth writing it here first so we can see how those same ideas manifest themselves in the full case. We only have a few different cases, okay? So the one that we've seen a few times, I feel bad for the people that have a robot directly in the way, but I guess of all the things to be occluded by, robots are good. Okay, so maybe I could do a PD control, right? PID control is perfectly good too, but I'll just do PD control for now. So what if I did KP Q desired minus Q, KD Q desired dot minus Q dot? That's one of the systems that we've seen before. You're right, sorry. No, it should be plus over here. Because I put the desired in, I put a minus here. Sometimes I do Q dot. There's absolutely an error, thank you. Good. So, by the way, this is well defined. If I have a trajectory a priori, I could take the derivative of that trajectory, right? And I could have a desired velocity at every instant in time too if I'm tracking some trajectory. Okay. So what happens if I put this controller even into my little mass system. Let's say I have a desired trajectory that was just a sine wave or something like this. Let's say q desired of time was just, I don't know, 10 times sine of t. I could certainly, figure out, I could take the derivatives, of course, right? Q dot t is just 10 cosine of t, and I could run this controller. How well will it do at tracking? What are the good and bad things about that? Assuming I've chosen pretty good values for, let's say, Kp and Kd, how would you expect this to perform? Yes?
Would that be like consistent time delay?
Good. So there's a question about delay, which we're going to, that's actually the second point I want to make. So yes, there's going to be a little bit of lag here. What about what if I just said the desired trajectory was 0? What's going to happen? That's even the simplest case. What if QD was just 0? What's this controller going to do?
Will it always be 90 degrees out of phase?
It won't be 90 degrees out of phase. That's a good question. I mean, if I've chosen a critically damped thing and I say the desired is 0, so Q desired is 0, Q dot desired is 0, then I will have a system that has a critically damped response, assuming I've chosen this. But the question is, does it get to the desired 0? And it doesn't necessarily, because there's an offset term here in the gravity, and this is fundamentally an error-driven controller, okay? So if Q equals Q desired, and Q dot equals Q desired, then the torque is 0, and gravity is going to pull me away. It requires some error here in order to resist gravity and balance. And I made the trivial simulation just so we could see it. Okay. Yeah, this is the simple case. Let's even make, it's easy to see when I just set the amplitude to 0. Okay, if my desired trajectory is just a flat line, and I have a point mass finger, and I have gravity, and I run a PD controller, then it will converge to a steady state, but it's not necessarily going to drive the error to 0. A PID controller would drive that to 0 if I put the integral term back in. But when we start tracking fast trajectories, the integral term is going to have a more complex effect, so I'm going to leave it out for now. There's a different way besides the integral term that we could take care of that. And I want you to appreciate that that actually is what happened when we wrote the stiffness controller before. Okay? So when we wrote a stiffness controller before, we wrote almost the same controller. But we also added in, actually subtracted off, the gravity term. Right? And we called that our stiffness control before. And I almost feel silly calling these things different things. In the point finger case, they're so simple, okay? But I think this is an important idea. One thing you can do, if you know the mass of your finger, is you can just subtract it off, okay? And the reason that intellectually matches stiffness control is because then I can say that the resulting closed loop dynamics were mq double dot equal plus, I'll do it like a mass spring damper, so I'm going to change my sign on that. Like Leray was looking for. This is a dot here now. Q desired equals 0, in fact, if there's no external force. Right? The PD controller has an extra nagging term from gravity. The stiffness controller, by virtue of trying to act like a spring, is actually canceling that out. But in the simple case, the only thing that's different between the stiffness controller and the PD controller is gravity compensation. Okay, and of course, if I add that gravity compensation into the simulator, then I get a nice response that will converge to the desired. When the desired is 0, at least. If I do something more interesting, like have it be the sine wave again, then this actually will do a fairly okay job at tracking. This is the orange is the desired, the blue is the actual. I start it a little bit off the nominal, and although there's a little bit of lag certainly at the beginning here, it actually does a pretty good job. I think I'd have to put up the bandwidth to see the phase. I'd have to increase the frequency to see any notable lag. Okay. It turns out you can do better still. You can get around some of the lag with just one additional idea. And guess what? That additional idea is what happens in inverse dynamics control. In the point finger case, it's all extremely simple. What would you do to try to get around that lag, if you will, which is, there's an extra piece of information that we haven't given our tracking controller. Which is we know arbitrary derivatives of Q, right? Of Q desired. If we tell it where it's going to go and give a feed forward term that says, that uses Q double dot, then we can do even better, we can get better tracking performance still. Okay? So there's a couple ways that you could add that in. The way that it's typically done in inverse dynamics control, I wish it was exactly the thing you'd expect, but for an important reason, it's just a little different than what you'd expect. But I'm going to say it's Q double dot desired, and I'm going to go ahead and multiply that mass by all of my terms here. Flipping my signs. Let's do it like this. So this is a feed forward term. And it's kind of fundamentally, it's what you need to do to get around this error-driven control. You want to be able to send it so that if the trajectory is on, if your current system is exactly on the trajectory, it will get the command it needs to stay on the trajectory. You don't have to wait for error to occur to get back towards the trajectory. The way to do that is by giving instantaneous information about where that trajectory is going to go. And this is what happens in inverse dynamics control. Okay? Super simple ideas, especially in the point finger case, and they're just going to map directly over to the joint, full joint robot case. And of course, I will try to convince you here that if I were to put the feed forward term in, that things get even better, that I get beautiful convergence to the nominal trajectory, and I'll stay on the nominal trajectory. I won't deviate on every oscillation. Once I'm there, I'll stay on there. It's actually easy to see that, okay? The reason to do this and have mass actually multiply I'm going to scale my Kp and Kd also by the mass, is because then if I write out the closed loop dynamics, I can say that I have mq double dot I can pull this whole thing on the other side here. Minus this. I'll just pull that on the other side. Okay. I'll put it in spring mass damper form again. I'll put my damping equals 0. Okay. That's the resulting equations of motion. And if I were to just call this term E, if I define E to be my error, I'll call it Q minus Q desired, then I could write this same equation, and you'll see this often in the multi-body manipulator control world. I could write the same equation as just a second order spring mass damper on the error. Okay, so the error will converge to 0 and stay at 0. And that's beautiful. Okay, and that wasn't true until I put the feed forward accelerations in. I want to make sure that these ideas are clear, because they'll get more, same ideas, but just with more terms and the like if when we go to the manipulator case. Yes?
So in general, is it true, like seems like you're assuming more and more stuff. Like for stiffness control, you need to do gravity compensation, and for reverse dynamic, you need to do one mass, and you need to be able to send desired acceleration.
Excellent. Good. So the question is, what are the requirements for the controller in terms of knowing the system, right? So in this case, I only need to know the gravity terms, right? If I have a model of the gravity terms of the robot, then I can execute this controller. Here, I applied a controller that had the mass also inside it, mass and the gravity term, okay? So that does ask me to know more about my system. But you can ask an interesting question about if this is approximate, how sensitive is it? This is actually relatively not terribly sensitive. You can do an error analysis of what happens if I put M tilde in like this. If you have controllers that try to invert mass and stuff like this, it can get a lot more sensitive. There's different ways that mass can enter. This one's not as terrible. Okay. The Q double dot is, so this controller doesn't need to sense Q double dot on the robot. It's just if I have a trajectory, I can differentiate it twice. That's my motion plan, I differentiated twice. As long as I could do that, that's okay. So I don't feel that I added a new requirement in terms of sensing in that. But there is a new requirement in terms of the model. Great question. This controller is actually the one we've been mostly using in simulation. It has torques coming out in the Drake systems framework, whatever. You'll see this as the estimated state coming in, the desired state coming in, and then you can send a feed forward acceleration coming in. That's the inverse dynamics controller. You'll see that in the manipulation station stack that you've been running. But we actually don't send, we just leave this disconnected because EWO won't accept it. And I'll tell you about that at the end, maybe why, okay? If I put force back in, then it's not so different. If I were to put the force back in, then I'd get a trailing force term, and it's interesting to think about what happens if I put the force back in. Now I have a second order damped oscillator, but with some driving external force. Okay, so maybe that's still a pretty reasonable thing to do. Yeah? Good, okay, sorry.
In reality, what sensor do we use to get Q double dot? Do we use numerical method from positions, or do we have after sensor?
Again, this is Q double dot desired.
Yeah, but like the next equation.
This is, Good, that's a great. So this is me analyzing the closed loop system. I don't have to, this is the controller that I implement. This is what I have to type in. The result of combining my controller with physics is something that uses Q double dot because physics uses Q double dot. But I don't have to implement that.
What about Q dot? Like we call it.
For Q dot, it's going to be, I mean, depending on the sensors, but there's, you know, rotary encoders there. Derivatives, we typically think of as positions and derivatives to be pretty clean, and we try to avoid accelerations as a general rule of thumb. You don't want to do high bandwidth control with accelerations. So EWA, you know, just something I was going to say later, but EWA allows you to send Q desired, but it doesn't actually allow you to independently send Q desired and Q desired dot. I believe I think they made a safety argument with that, and that somehow, if you could imagine a bad user sending inconsistent Q and Q desired dot, that might break their safety proof, for instance. So they instead take a sequence of Q desired and they add a little bit more delay even, and they'll take a finite differences to estimate Q dot and then send that as a command. But you're only actually allowed to talk to the robot with Q desired over time. All right, so let's blow this up now so we understand in the simple case, PD, stiffness, and inverse dynamics. It's just adding one thing at a time. Yeah? For which part? They shouldn't. The stiffness control, the tau g. So they should both be minus tau g. Thank you. Because, yes, the tau g is on the right-hand side with the u's, so I have to subtract it out. Thank you for catching that. Too many symbols to get right on the board. Okay, same recipe now, but let's do it on the manipulator equations. Remember, the dynamics that we were writing was just mass times acceleration equals the sum of the forces. The way that manifests in the manipulator equations is now my MA is just a little bit more complicated. It looks like this and this. Okay, these are this is now the inertial matrix. These are the Coriolis terms, but they really go together. This is M. You should think of this together as MA. If you were to change the coordinate system, then they would both change equivalently. This is MA. Okay, and then we get the sum of the forces. So you get the gravity forces, which in general are some function of the configuration. I'll assume that I've got U's everywhere, so I'll just say I can command every coordinate. And then I can have, I'll write it as a torque now, a tau external. Okay, so the first thing I want to ask is just in joint space, how should I do trajectory tracking? If I have a desired QD of t, and now I have these equations, then what's the analogous thing to do, right? And it follows exactly from what we do. We could do PD control, right? Which actually looks identical in this case. It's just now it's identical. I shouldn't even spend my time writing it, maybe, but. The stiffness control also looks effectively identical. It's just canceling out a more interesting gravity term. Minus tau g, which is a function of q now. And the resulting dynamics of that are a more interesting version of what we've done before. But it's still it's just a more complicated spring mass damper system, and it happens in the joint coordinates. So what does that mean is if I put a resistive force, if I push on a particular joint, I expect it to feel like a spring when it's pushing back at me. Okay? And these terms are the mass of that spring mass damper system, and they're a more complicated object, but it should still feel like if I were to move one joint at a time, for instance, it should feel like I'm pushing against it. And we're going to actually do that. Terry, is it okay to do it now? Yeah? Let's do so I want you to at least see me feel we'll do the joint impedance control, okay? Now, so EWA it's called joint impedance control, okay? But like I said before, it doesn't shape the mass of the robot, it only shapes the rotor mass. So unless you get to the level of modeling the rotor inertia and the elastic joints, at our level of modeling, it looks like a stiffness controller. Okay, now let me just say something about safety here. So we're only running the very simple controller that has been actually certified, and Terry's got his hand on the big red button. But I don't advise, in general, people running up and touching powerful robots, okay? I'm going to just do this carefully. So right now, this is in joint impedance control mode. So that means if I were to apply, it's got something like a 50 Newton meter, I think was the gains we put in here, a 50 Newton meter gain on any one of those joints. It's going to let me move it, right? I can kind of move the robot around. It's going to resist. It's going to drive itself back to this nominal joint configuration. But it's in a complicated space, right? The response is a complicated function of the kinematics of the robot because every joint independently is looking like a spring. Okay? It's pretty beautiful, and it feels very nice and natural and smooth, which is a testament to the hardware, okay? Good, we're gonna do the other one in just a minute if that's okay, yeah? So that's, I think, at our level of modeling, this is kind of what we should think about EWA as doing. If you wanted a higher fidelity simulation model, if the reason your robot was failing to pick up a coffee cup was because of the dynamics of the elastic joint, then you have to go dig deeper than this. But for almost all the manipulation research I've done, you haven't had to go to that level of modeling power, okay? You can do inverse dynamics control too, and we often write it down. It's interesting though that that EWA doesn't do it, and I think it does go back to the requirements, as you say, of what's happening. The inverse dynamics controller would send in, I'm going to take a mass times the entire signal here. I'll send in Q double dot desired as my lead, my feed forward term, and I'll put inside here my Kp plus Kd. Outside here, I'll take my tau gravity, okay? And the result is once again a beautiful system I keep switching my E dots and whatever, but it looks like this. that the error dynamics in joint space will converge like a second order spring with a more complicated mass matrix to the, it actually has the Coriolis terms too. Like I said, those two go together. Those are still there, okay? But it's a more complicated mass spring damper system, but the error converges to 0. So this is a nice way to do high-end trajectory tracking control. If you had a torque-controlled robot and you wanted to do extremely accurate trajectories, then I recommend sending in the Q double dot forward. I think it's only doing first derivative. It could be taking two finite derivatives, differences of my Q command. But I don't think the advantage is there when you've already done a lag. So I suspect it's not. Okay, so the interesting differences now become when we start thinking about how the forces enter the joint equations, okay? The multi-body equations. Because forces naturally live in Cartesian space, and everything here is in joint space. In joint space, it just looks like a more complicated finger, if you will, and everything still goes. But let's see what happens if I add forces in. I showed you once before when we were talking about friction cones and whatever, I showed you these equations without fully justifying them. The way that forces enter the multibody equations, I wrote this down sort of quickly without justification, that it looks something like this, yeah? That I have a Jacobian transpose times F, where this is a Cartesian force. But these equations live in joint coordinates, right? If you have a robot with some joints and some equations of motion, and you apply a force, a Cartesian force here, then the question is, how does it affect torques at the links? Or vice versa, if I were to apply torques at the links, what sort of force would I be applying at a point on the world? Okay. And the relationship here, which is there, but more generally is that you have this relationship of torque has a Jacobian transpose times force. And that's that one I want you to remember. That's like a good thing to know at parties, I guess. And it's like, yeah, I think that's core knowledge, I would say. How many people know why torque is Jacobian transpose times force? Yeah. Okay, I'm going to add to your core knowledge. It's really simple. Okay, it's just a power argument. Okay, so there's if you think about the work actually done at the end effector, this is the way we think about it. So if I have a robot in some configuration, I want to think about the incremental work done at this point on the end effector. Work is force times distance, right? This is an argument of virtual work, it's called. Work is force times distance. Okay? I'm going to compute the work done at the end effector in two different ways. I'll think about a virtual change in x, and I'll think about a virtual change in q. Okay, these are two different ways, and I should get the same answer. Okay, so the total work done by the force should have an equivalent work done by the torques. Okay, so if I say the force, let me use my correct small f, dotted with some delta change in x, must equal the torque dotted with some virtual change in q. Okay, so this is a virtual displacement in x. This is a virtual displacement in joint. Okay, this delta notation. And that's a dot product. Since we also know that delta x is related to delta q by the sum Jacobians, then if you put this together and say it has to work for all delta q, I have f, and I'll go ahead and multiply out the transpose. I'll say f transpose equals Jacobian q. Delta q is tau transpose delta q, and this has to work for all delta q, then it is equivalent to saying tau, and I'll take a transpose on both sides, is J transpose F. So anytime you want to go between a force computation at a particular point and a torque at the joints, the Jacobian is exactly the mechanism you need, these Jacobian transpose. Okay, it's just an argument about virtual work. It's actually I think a major advance in sort of the rigid body mechanics when people started thinking about these virtual displacements, and that's the Lambert's principle and all the good stuff, all the variational mechanics work. So there's a lot of depth there, and the reason for those annoying virtual displacements is actually really important and the like, but I think it makes for simple algebra, and you get tau equals Jacobian transpose times force. Okay, so let's think about now trying to live in this space. Remember, the amazing thing we want to do if we're thinking about forces is we want to make the big complicated robot act like be able to control the forces as if it was a point finger. So given we have this relationship and we see how it enters the multibody equation, how do we make that happen? It turns out this translation between the Cartesian space and the torque space with the Jacobian transpose can actually be applied to the entire multibody equations. And the result of doing that is one of the most beautiful results on our list here, which is this idea of writing Cartesian space dynamics, task space dynamics. Okay, so now my location of my finger, I'll call it an end effector more generally here. So this will be my end effector frame. We know that that is related to Q by the kinematics. My velocities are related by the Jacobian. My accelerations also have the relationship, v dot of E, which we actually have multi-body notation for A, calling that A, and that gives me, if I take the time derivative one more time, I get this plus an extra term, J dot Q dot. The tricky step here is if I take the multibody equations, solve them for Q double dot, and insert them into this equation, then I actually get a new set of multibody equations. The derivation's in a little bit more detail in the notes, or at least certainly all the terms are written out there. Keep that off just to keep it simple. So what is this equation? This is the manipulator dynamics from the point of view of the end effector. Okay. This is my command input. I can just achieve this with my Jacobian transpose. And I can actually write the dynamics as it's viewed from the finger. Okay? From the end effector. And since these equations, so this thing has the original mass matrix in it, it has a couple of Jacobians in it, it has a couple inverses in it, but it's always well posed, assuming, it's actually always positive definite. It has some nice properties, okay? And all of these are just functions of the original equations and the Jacobian. It's basically the Jacobian transpose applied to all those equations. But these equations, looking at the dynamics of my robot through the lens in the coordinate system of the end effector, look so similar to what we've done before that I can use the same kind of control. In fact, I could write a stiffness controller the same way I did before. I just will cancel this out. I'll write the PD terms on this. And the resulting equations will be an end effector dynamics that looks like a spring mass damper system. Okay? That's the amazing thing. So this is Cartesian stiffness. This is the analysis, but the controller is simple. It's still just, I'm going to do my KP. I have to modify it into the correct space, but in this coordinate system, the controller is simple. I'm going to write it as PE minus PE KD P dot E minus P dot E, and then minus this F of gravity. Okay. Now you see why I was worried about snowing you with the details, right? So, but I hope you see by the simple analogies that this is really just writing the PD controller, canceling the gravity, but we're doing it in the coordinate system of the end effector dynamics. It's fantastic. Okay? Should we run it, Terry? Is that good? I showed you the KUKA folks running this early, and they looked happy. So I figured I should try it. Maybe I'll be happy. Again, this is just one of the basic certified controllers, okay? And which one we're doing the translational? So the way to make this interesting is we put a different translational stiffness in X, Y, and Z, yeah? So I think it was 150, 250, and 50 or something like this, right? So one of them is going to be really, that one's a little bit, that's the 250, and then this is the 50 Newton meters. Yeah?
If you want to go from Cartesian back to the joint space, then you need to solve some problem to like map it back to the joint control, because it's like 6 degrees.
Okay, there's two parts of that question. So the controller that I've written here, I can actually just command Jacobian transpose times this a virtual force. So I don't have any ugly inverses in the control. But you're right, there's a null space of that control. And I should do something, if I have more degrees of freedom than the thing I'm commanding, then I should do something in the null space to not leave that undefined, right? But the actual forward mapping looks good. There's no inverses in the forward mapping. Okay, so just once more. So what is also different compared to, remember before I was doing the joint by joint, and the response in the end effector was actually pretty complicated because it was living in joint space. The springs were living in joint space. But now it really does feel, obviously different and obviously, kind of linear. I mean, I don't know if I can feel linear, but in the end effector coordinates, right? That's why he was happy. That's pretty good. Okay, and then we can do the same thing in rotational coordinates. So all the same things work if you were to use our spatial vector notation and say that the thing I'm trying to control is not the position, but the orientation, or in general, spatial velocities and frames in the end effector. Then you can put a stiffness. You have to be a little careful at how you write stiffness in 6. I actually cited your paper actually about maybe an interesting way to write a 6 degree of freedom stiffness. Okay, but now if I wanted to push it sideways, he made it very stiff in the XYZ direction. So that end effector wants to stay there, but it's allowed to be soft in the out of plane. And I've got a smaller moment arm to do the last one, but yeah? It's math. Math works.
It's just related to the 6-dot rotation. So the angular velocity is S as angular rotation, and then you're testing solar angle.
There are different ways to write the stiffness. How do you parameterize the stiffness in that box? It's just the, what does it take a?
Talking about units?
The orientation stiffness, is it diagonal matrix on RPY?
I think so,
Yeah, I think it is, but I actually don't remember. So.
Studio also was RPY.
Yeah, they do RPY. Okay, yeah, so don't, I won't try to get to pi over 2. Awesome. Thank you, Terry. Okay, questions about that? Yes?
It might be a naive question on this one, but so EWA doesn't take in acceleration commands.
Correct.
Is there a way to use force control to follow a trajectory?
Good. That's not a naive question. That's an advanced question, I would say. So remember how I said you can mix this with in the hybrid position control? So EWA will actually also accept a feed-forward force. We normally live in joint. I know better what it does in joint. I assume it could also take a feed-forward force in Cartesian, but actually I'd have to look to make sure that. We almost always use joint space control for a limitation I'll talk about in just a second. So yes, if you're in the limit, you could set Kp and Kd in the joint space impedance controller to 0. You can say, I know everything I should know. It will still compensate torque for you, the gravity torque. And it actually does a little bit more. It compensates friction, too, in a very clever way. But then you can command forces directly to add in. Therefore, you could do the acceleration-based stuff through that. I think the bandwidth needs to be considered. So expecting it to track super high through that force command is to maybe, there'll be limits to what you can do. Did that answer the question? Yeah, great. Okay. Yeah, so this is super powerful. There's only one thing that I don't like about it. Does anybody, what's the one thing I don't like about it? I kind of alluded to it in that question. I mentioned it once before, which is why it's a fair question. What's that? The null space is, I think that's manageable. You should just, so, in fact, I should probably have lectured about that. Because it's sort of a thing. It's called operation space control, right? And the idea, so we talked about joint centering in differential inverse kinematics. There's a joint centering. I did put it in the notes. There's a joint centering sort of version for this. I can say it off the top of my head here. How would you do joint centering to take care of that null space? If you're normally commanding this with your command that comes from stiffness control, and you want to take care of the null space, then the standard thing people would do would do This is the null space projection. And then write something like Kp q minus q desired minus q lots of symbols, but the point is you could write it like a PD controller and have it in the joint coordinates and project it into the null space of this. So that's a really beautiful idea that says, in some sense, and the way people talk about this, this is the first priority task. The torques you pick should absolutely create the virtual stiffness that you want at the end effector. But in the null space of that Jacobian and any extra degrees of freedom, then I'd like the rest of my joints to act like they're a PD controller going back to the original. Okay? And this mixing of joint space and end effector space control was originally, it's called operational space control. And operational space control has grown into a whole, sort of rich library of ways to prioritize different different tasks and constraints. And there's humanoid versions of it and the like, but operation space control was originally this just, let's mix joint and force into the same framework. Great question, but that wasn't my biggest concern. I have exquisite control. I can write the dynamics beautifully, but I have to know the point about which I'm going to write my dynamics. That's the thing that drives me nuts. Okay? All of this is based so heavily on the Jacobian, and it's the Jacobian that gets me from robot joint coordinates to a particular point on my robot. Okay? So if I'm in the factory or something and I'm applying forces exactly at the end of the orange knob on the robot, then life is good. Okay? I can act exactly like I want at the end of that orange knob. It's actually the center of the center of that little orange sphere, I think, is where the coordinate system is for us today. All right. But if the robot bumps into something halfway up its elbow, then we haven't solved that problem. We haven't programmed the response that the robot's going to have if I were to go up. It's turned off right now, but if I were to go up and knock it like this, none of my math has told me what that response should be if I've programmed the response down here. And it's for that reason that we tend to live in joint space, because if I get a perturbation anywhere, it might not have a beautiful interpretation at the end effector, but it has a logical interpretation in the joint coordinates. Okay? You would like to say, there's a richer problem of trying to say, like, how would I program the response for whatever contact I happen to be experiencing? That's a rich problem, and I'll maybe jump ahead and say that too. I didn't even show most of my videos here. Okay, so there's an interesting problem of contact estimation. If we know J transpose F equals torque, then you can ask the question, if I'm feeling torques that I didn't expect at my robot, where on the robot did that force come from? Okay? And you can imagine if you can estimate by looking at your joint torque sensors where on the robot you made contact, then you could program the response to interact at that point with some impedance or some stiffness. But it turns out that's a really bad problem. I think this picture was one that Pang made to try to make that point. If you are experiencing some joint torques and you try to map that back to the possible locations on the arm, and you admit that there's a friction cone on the arm, so the location, the direction is not directly imposed by the location. It could be, even if I'm pushing here, it could be any of these vectors. And you try to solve the inverse problem. For a particular torque, there's a bunch of places on the robot that could have possibly, this wasn't even the worst one, I think, but now that I'm seeing it, but there's a lot of different locations on the robot that could have explained the same torques. And in general, I think you can make some progress. The people that have done really nice contact estimation have done it well enough that you can stop when you're about to hit something, but not well enough that you can program the response at an unexpected location, right? That's a hard problem, especially if I were to allow the fact that there could be multiple points of contact, then it gets very complicated. People who've been asking about human-robot interaction, right? If I bump up against something and it's a wall, then the thing I should do might be very different than if I bump up against something and it's a person, in both directions, because actually the person might be trying to command me, right, by pushing me around, and I should be submissive, I guess, to the human, right? Or it could be other cases where I should try to get the task done even through some, so it's a very, very hard problem. I think the world is sort of agreeing that maybe the way to solve that is with tactile skins, and that's one of the things we're excited about with the soft robot project at TRI is we're trying to build sensing skins, and I think at some point you have to try to estimate the contact location with a richer set of sensors than just your joint torques. I think we understand that the joint torques are not going to get it done unless you had a lot of links. Okay, so I'd say that's the biggest limitation of this is the impedance control, stiffness control, end effector view of the world needs you to know where the end effector is. And that's why, so if I now go back to this one example I talked about it with key points, it's kind of exciting to think about maybe combining some of the tools from perception with some of the good tools from control, right? So the simplest version of this, I would say, would be that if we're looking at a tool and we want to apply a force at the end of the tool instead of the end of the end effector, if I use my sort of key point estimation pipeline, if I want to control a stiffness in multiple degrees of freedom, maybe I'll have an oriented key point or a handful of key points so that I can get the orientation of the object too, okay? And then if I assume the object is fixed to the hand, I just have a slightly different end effector on my robot. I have a Jacobian that's just slightly different, but based on the location that came out of the key point estimator, and I can suddenly apply impedance or stiffness control at the end effector of the tool, right? And that's what made the examples I showed that of erasing and plugging in and things like this. This was impedance control plus key points. I think there's probably lots of potent combinations of the different tools, but you do need to know where the location of the contact is in order to get that done. Okay, yeah, and so what do we do on the EWA? We are sending in only Q desired trajectory, like I said, and EWA's controller is differentiating. We don't get to send the feed forward. Differentiating. We tend to do joint stiffness control. Despite the elegance of the Cartesian stuff, the joint stiffness is, it's more robust to unknown contacts, I think, or more reasonable response. Principle of least astonishment, if you will, responses to unknown contacts. And an important point that I maybe forgot to make, but the difference between the stiffness control, which is canceling out gravity, versus just a PD control, is if I can cancel out gravity with a feed-forward gravity term, then I can choose my stiffnesses to be much softer. I can choose KP and KD to be much smaller if they don't have to also fight gravity. And that's how we got compliant motion for things like opening up the dishwasher door. The trajectory of this was, I would say, carefully planned, but with a highly imperfect model of where the dishwasher door is, where the hinge on the dishwasher door was, and we are heavily relying on the ability for that robot, just like when I pushed it in joint space mode, to deviate from its planned trajectory in order to execute that task. If it didn't, if those gains were too high and the robot was pulling down on this and it was kinematically bad, the hand could get jammed and things would be bad. You'd blow a fuse. These things are pretty robust. Good. Any other questions about them? Did that lineup of, did that organization help with the litany of different versions? Okay. Cool. I don't mind ending a few minutes early, and I actually have one other thing. If anybody wants a Drake sticker, someone gave me Drake stickers, and I have laptop-sized Drake stickers and cell phone-sized Drake stickers. And if you guys come to class, you get to get Drake stickers. I mean, just take one or two. Okay, see you next time.